let's just try to understand the importance of quantum mechanics, why we want to study quantum mechanics, okay, and all those stuff. So before I start with that, okay, let me tell you a very brief idea of how the world is divided into and which laws are applicable where, right? So we know that if we basically consider our world, our day-to-day life, okay, we can divide it into two sections. One is the microscopic world. So that means you are going into the atomic scale, and the other one is the macroscopic world. Macroscopic. Now, when we look into our lives, day to day, whatever we observe, which was actually being observed in ancient times, because at that time, instruments to observe the atomic level or the molecular level were not developed. So everyone looked into only the macroscopic world, and there, whatever laws were used were classical in nature. So that means if I want to use classical mechanics, I am looking more or less into the macroscopic world. Now, if I go into the microscopic world, and as you know, the word microscopic and microscope are very much connected. It comes from the word microscopic, microscope. We go into the atomic section, and there we see that whatever classical laws we know are not applicable. That means in the microscopic world, we are going to use quantum mechanics. I'll give you different examples where you will see that this idea of quantum mechanics is also applicable in the macroscopic world or in our day-to-day life. So that means under certain limiting conditions, you can use quantum mechanics even in the microscopic world. But classical mechanics cannot be used into the microscopic world. So if we want to understand how nature works, we have to understand quantum mechanics, because any working phenomenon basically starts from the atomic level. So if we want to study quantum mechanics, we should study the atomic world. So whenever we are going to study the atomic world, we are taking quantum mechanics. Now, quantum mechanics has got a lot of application in modern physics. Talk about atomic and molecular physics, it's a part of modern physics. You talk about nuclear physics, it's a part of modern physics. And both of these are nothing but talking about the atomic world. That means we have to use quantum mechanics there. And that's why quantum mechanics is important. Whatever happened after 1900 and when quantum mechanics started growing, it actually became a very integral part of modern physics. This entire idea of quantum mechanics is actually based on probability. Now, I'll give you a real life example where classical mechanics and quantum mechanics both are applicable. Okay, you toss a coin and you are expecting a head or a tail. Okay, so India and Sri Lanka are playing the test match today, so we have won the toss. So head tail. So can we use quantum mechanics here? The answer is yes. As soon as the coin is flipped and it's in air, we don't know whether it is going to be head or tail, right? That is quantum mechanics. But as soon as it lands on the ground, I look into it, I say, oh, it's a head or it's a tail. I know the state, it's a definite state. That's classical mechanics. And that's the idea of probability. I can say, okay, looking into the weather report that it's going to rain today or it's not going to rain today. But I cannot be certain 100% that it's not going to rain today. There is a probability. 99% is not going to rain, but 1% chances is there that it's going to rain. And that's the uncertainty that creates a confusion in quantum mechanics. But let me tell you, it's a complete physics in itself. So it's not that quantum mechanics is vague. It's not vague. It is telling you the real world, okay? Because, when people gave their theory, for example, let's talk about any theory, Thomson's model, plum pudding model, Bohr atomic model, it explained certain things. The entire thing was never explained. And they said that, no, this is not correct. This is not the right atomic model. What did people do then? They started studying, and when quantum mechanics came into the picture, now we know that if we basically have a nuclei and if we have an electron, this electron is not going to move in orbits. That's not true. It's basically going to have a cloud. There is something which is called an electron cloud. That means if I want to find out the position of an electron at a certain time, I have to use quantum mechanics, and using that quantum mechanics, I can say that the electron is at this position with certain probability. That is the probabilistic idea. That means it's not certain that a pinpoint where the electron will be exactly around the nucleus. So it moves around a cloud which is called the electronic cloud. So the latest atomic model which is valid and explains everything, most of the things, because we have not yet discovered everything, is very difficult to know how nature works. But most of the things, that means the latest model is the quantum atomic model. That's something which is valid today. Okay, it's not that Bohr model, Thomson model failed totally. It didn't fail totally. It was able to explain certain things, but not the entire thing. Okay, so it's very difficult. So there also we have quantum mechanics. So that means quantum mechanics is something which we have been studying from for a very long period in our class. Okay, for example, if you remember your class 12 Young double slit experiment, what was it all about? It was about interference. We basically have two slits or two small opening, and we have got a wave coming in, and it hits those slits and gets divided into two different wave fronts. Wave and wave fronts, I think you know the connection. So wave fronts will represent those waves. So these are the wave fronts, and they also interfere. And if you look into the screen, you are going to see a certain pattern of dark and light band. That is actually called an interference pattern. But what is that property? That is the wave property. At the same time, we have also studied about photoelectric effect. That means if that electromagnetic radiation, maybe a UV radiation, falls on a plate, maybe a metal plate, maybe a copper plate, it will eject electron. That is photoelectric effect, and that is actually the particle nature of the wave, of the electromagnetic ray. So it has got both particle nature as well as wave nature. How can the same thing have two different natures? Okay, and that is also something which is supported by quantum mechanics. It depends under what dimension you are considering. So this is something which we are going to study later in our syllabus. So it's not that you have not studied about quantum mechanics. These are all nothing but explained by quantum mechanical phenomena. Today we are going to start with quantum mechanics specifically. Okay, so this is the beginning of quantum mechanics. So when did quantum mechanics actually started? It actually started in the year 1899. Okay, you cannot say it's a fixed point where it started, but at that time people started to think about a new theory because classical mechanics was not fitting into the experimental result. So in 1899, the idea of blackbody radiation was given. Okay, so what is blackbody radiation? In plain simple word, it means that you have got some electromagnetic radiation falling on a body, and it will absorb all those radiations. It won't emit any of these radiations. It can only be emitted when the temperature of that body is raised. So maybe at room temperature, it will emit some radiation. If you raise the temperature to 100 degree, it will emit some other radiation. So if you want to emit all the radiations from the black body, you have to raise the temperature to different points. Okay, and that is actually an idea of black body radiation. So if you look into the nature, the closest example would be graphite. Graphite is a very close example of a black body, and if you want to have a black body in the lab, what is done is basically, it's colored in pitch black, a spherical shape, and there is a very small opening in front, and the light is allowed to go inside and hit. And as soon as it hits, it will get reflected and it will suffer multiple reflections, and that particular electromagnetic radiation will get lost within that spherical system. That is actually mimicking a black body, but again let me tell you, the chances of it coming out is minimum, but still there are some chances that it will come out of it. So this is again not a perfect black body, no perfection. Okay, perfection does not exist. Okay, that's very difficult even in science. So recently, if I'm not wrong, please check. Okay, Google, I forgot the year, maybe it's 2018, when in the lab they have developed a black body and it named them as Venta Black. Venta Black. It was developed in a lab. Okay, so it was done. It was actually very close to a perfectly black body. And graphite and Venta Black probably are the best examples of black body that we have today. Out of which Venta Black was developed in a lab. It was man-made and it is done in 2018. Okay. So before I proceed with the next topic, let me just tell you a bit about black body radiation. So what happens in black body radiation is, I will need some space, so maybe I will rub these things off. Okay, ye wale to you already know these things, right? So what happened was, experimentally observations are always made, and if something is experimental, we know more or less it's correct. There are theories provided, And then if it does not agree with the experimental result, that means that theory is wrong. Straight away we can discard that theory. But experimental results are not wrong because this is how nature works. And that working of nature was observed experimentally. So what happened was, experimentally a graph was plotted between energy and wavelength. That time people didn't knew what is the relation between energy and wavelength. Of course today we know that energy is equal to h nu, okay, or hc by lambda. That means energy and wavelength are connected. But that time it was not known. What people knew was we can actually plot a graph between different wavelengths and how much energy was emitted for a particular body. And the graph actually looked something like this. Okay, it's not perfectly normal distribution there, so I'm just drawing it approximately. And at a certain wavelength, okay, the energy was maximum. Let's say lambda m2, and let's say the temperature was T2. So you know, if you have a normal body, if you raise the temperature, it's going to emit more energy. If you decrease the temperature, it is going to emit less energy. That's quite obvious. Now, if the temperature T2 is greater than T1, that means T1 is a lower temperature. If the temperature is lower, it's going to emit less energy, but then the peak will be there, but the peak will be shifted towards the higher wavelength region. So this one I will mark this as lambda m1, and this is at temperature T1. So what do I see? That if the temperature is more, the wavelength is less, the peak wavelength. Okay, that means that wavelength and temperature are connected. This is just an interpretation experimentally observed, and they are inversely proportional. Temperature is more, peak wavelength is less, temperature is less, peak wavelength is more. That means that this temperature into wavelength measurement, peak wavelength and temperature measurement is basically a constant. This was actually called Wien's displacement law. I'm not going to give you the expression or the constant value, you can calculate it, but that is not needed, because let me tell you, this is not the part of your syllabus. I'm not going to probably ask you much questions from this part, but this is very important to understand or appreciate the importance of quantum mechanics. Why quantum mechanics came in? This is actually called the Wien's distribution law. Okay, so this is everything about this curve. So this curve was experimentally observed. There was no theoretical interpretation given for this. Later on, the theoretical interpretation started. What are those theoretical interpretations? The first theoretical interpretation was Wien's distribution law. Let me take a different color. He has given an expression, equation, okay, connecting E lambda and lambda. And when the graph was plotted, you can easily plot a graph using any computer programming. Okay, you can check it also in Excel sheet also. You can check. When the graph was plotted, it was seen that it agreed with this part. There was no issues. But then it went straight up. It didn't come down if a graph was plotted using the expression given by Wien. So this was actually a theoretical result, this graph, and this was actually given by Wien. That means it agreed for low wavelength region. Okay, let me just scroll down a bit. I've written the sentence here, you can check. Wien's distribution law holds for short wavelength region. That means when lambda is less than lambda m. Whatever wavelength you are considering, lambda, it is less than the maximum wavelength. There this law was valid. So that means it failed because it did not explain the higher wavelength region. Then came Rayleigh and Jean, another set of scientists, and they have given an expression with this part. With this part. This is again theoretical, and this was actually given by Rayleigh and Jean. So that means here it agreed with the other side of the peak. So that means this explained this partially, this explained this partially, but this entire curve was not being explained by any of the laws. So Rayleigh-Jean's law was valid for longer wavelength. Who gave the solution to this? This solution was given by Planck. Planck gave a distribution law where it was valid for the entire range. That means Planck gave an empirical relation. Empirical relationship means you are making the relationship looking into the experimental result. So it's basically an interpretation. Okay. Planck gave this empirical relationship, and his relationship fitted in exactly with the experimental result. What did Planck assume? Planck assumed that the energy that is being given out by a body is in the form of packets. These packets are called energy packets, and he gave the idea E is equal to h nu. Okay, he used this concept of E is equal to h nu. Now let me tell you what do you mean by energy packets. You go to a shop to purchase milk, and the shopkeeper sells it only in 500 grams or 1 liter. Okay, it doesn't sell it in 700 grams. So you cannot go and tell him, you give me 700 grams of milk, because he's not sending it in, selling it in that quantity, right? So that means it's in quantity, half liter, 1 liter, 2 liter, 1.5 liter, and so on. Similarly, when a body emits energy, it cannot be any energy. It's not a continuous value. It's discrete packets. That means it will be a function of frequency, h nu. It may be 1 h nu, 2 h nu, 3 h nu, 4 h nu. It cannot be half h nu, 4 by 3 h nu, 5 by 7 h nu. Not possible. It will be multiples of h nu. That was the Planck's idea, and based on this, he has actually given this theoretical explanation, and he has given this relation. Now, if you plot a graph for different values of lambda between energy and wavelength, you are going to get that experimental graph. Looking into this, straight away you might say that how can it be possible, because I see that lambda is at the denominator. That means as lambda keeps on increasing, energy will keep on decreasing. So if you look into it, at first instance you might feel that this is only going to explain the higher wavelength region. The answer is no, because it has got a term e to the power hc divided by lambda kt. So if you fix the temperature, this lambda will vary, and this is an exponential term. So if this keeps on increasing, this will also keep on decreasing. So at some point there will be a peak, and then it will change. Okay, so that's the reason that this entire relationship will explain this curve. You can plot a graph for your own satisfaction and check it also in maybe Excel or somewhere, or MATLAB. Okay, so what did Planck say? Planck said that these atoms and molecules will absorb or emit radiation in energy packets, and these energy packets are called photons. We are surrounded by energy, UV rays, electromagnetic waves you consider. Under that you have UV rays, visible light, infrared, and so on, right? Everything is having those energy packets, and these are in the form of photons. Okay, so the important conclusion is the energies of these atoms are quantized. This was a concept which was not explained or not understood by classical mechanics. Because when we say energies are released from a system, that means they are released from an atomic scale, which classical mechanics could not explain, and that's why quantum mechanics is very important. So this idea of blackbody radiation was a stepping stone for the beginning of quantum mechanics, and that is why we should study quantum mechanics. Okay, it's a very important topic, quantum mechanics. So it was actually not the end. Okay, people kept on working on quantum mechanics, and different theories were given. So you know, Einstein's famous photoelectric effect, if you go to 1916, okay, or 1905 actually, it will be 1905, the photoelectric effect came in, right? And then we know that was actually explaining the particle nature. There were scientists, you know, Millikan's oil drop experiment, if you remember. Millikan actually denied this fact. Millikan tried so many experiments for 10 years to disprove Einstein. He said that no, light cannot have particle nature, it will only have wave nature. He was in total favor of this wave nature. His attempt to disprove Einstein, in the process he has discovered and invented so many things that he got Nobel Prize for that later. Okay, so that's actually a different story. But then in 1916, Millikan also performed this experiment, Millikan's oil drop experiment, to find out the charge of electron and all. Okay, so those were there, which because of which also you also got the Nobel Prize. Okay, so you know these things came up. So scientific community, when you have these healthy arguments, there are things which actually are better for the humankind. So other quantum effects, maybe you can talk about Compton effect. Compton effect is also a quantum mechanical phenomenon, right? So Compton effect you might have studied in your lower classes, that is also there. And then we are going to discuss and talk about de Broglie wavelength in detail, okay? We will observe that you and me having some mass will also have a wavelength associated with us, okay? Wave particle duality. That means, you know, if a wave can behave both as particle as well as wave, okay? If a, you know, let's say we have got a radiation which will both have the wave property as well as the particle property. In the similar way, a particle should also have some wave property. Okay, if a wave has a particle property, a particle should also have wave property. So this is something which was actually proposed by de Broglie, and he has given a lot of ideas based on this. And then you know, Davison and Gaba, J.P. Thompson also has done their experiment which actually showed the wave nature. So this is something which we maybe will discuss, but we are not going to go into the detail because that is not a part of your syllabus. But something which is very important in your syllabus is Schrodinger equation. So Schrodinger equation is also something which we are going to study because, you know, physics is a bit handicapped without mathematical explanation. Physics and maths are married, as you all know. So if I have a mathematical explanation to this wave nature, this was actually being provided by Schrodinger. So Schrodinger equation is something which we are going to take up, and this will actually explain a probability of the existence of a particle within an atomic system. Okay, so this is something which is we are going to do in our coming classes.